Welcome to our deep dive into BERT, one of the most groundbreaking models in natural language processing. BERT didn't just improve language understanding, it completely revolutionized how machines comprehend text. Today, we'll unpack this architectural marvel that changed everything. Before BERT, language models were like reading a book with one eye covered. They could only look at words from left to right, missing the full context. Imagine trying to understand the word bank in I sat by the riverbank versus I went to the bank to withdraw money. Traditional models struggled with this because they couldn't see the complete picture simultaneously. BERT changed this by introducing bidirectional understanding. It can look at words from both directions at once, just like how humans naturally read and understand language. BERT stands for Bidirectional Encoder Representations from Transformers. Let's break this down. Bidirectional means it reads text in both directions. Encoder refers to the part of the transformer that processes input. Representations are the rich contextual embeddings it creates, and transformers is the underlying architecture that made it all possible. Released by Google in 2018, BERT achieved state-of-the-art results on 11 NLP tasks and became the foundation for countless modern language models. What makes BERT so powerful? First, it's pre-trained on massive amounts of text. Essentially, it reads the entire internet to understand language patterns. Second, it uses self-attention mechanisms that allow every word to directly interact with every other word in a sentence. Third, it's designed for transfer learning. You can fine-tune it for specific tasks with relatively little data. And fourth, its bidirectional nature means it understands context from both past and future words simultaneously. BERT's impact has been phenomenal, from search engines that better understand your queries, to chatbots that provide more relevant responses, to content moderation systems that catch subtle nuances. BERT and its variants power much of the modern AI we interact with daily. In this course, we'll explore BERT's architecture layer by layer, understand how it processes text, examine its training methodology, and see how to implement and fine-tune it for real-world applications. Let's begin by understanding the core problem BERT solved and why bidirectional understanding was such a breakthrough. Now let's peek under the hood of BERT and explore its architectural brilliance. BERT is built on the transformer architecture, specifically using only the encoder portion. Think of it as a sophisticated pattern recognition system with multiple layers of attention mechanisms working in harmony. BERT comes in two main sizes, BERT Base and BERT Large. BERT Base has 12 transformer layers, 768 hidden units, 12 attention heads, and 110 million parameters. BERT Large scales up to 24 layers, 1024 hidden units, 16 attention heads, and 340 million parameters. Each layer consists of a multi-head self-attention mechanism, followed by a feed-forward network with residual connections and layer normalization throughout. The magic happens in the self-attention mechanism. Imagine you're at a party and you want to understand a conversation. Instead of listening to just one person, you simultaneously pay attention to everyone speaking, weighing how relevant each person's words are to understanding the overall context. That's exactly what self-attention does. Every word in a sentence simultaneously attends to every other word, creating rich contextual representations. Let's trace how BERT processes text step by step. First, input tokens are converted to embeddings, numerical representations of words. But BERT doesn't just use word embeddings. It combines three types: token embeddings, the actual words; segment embeddings, which sentence the word belongs to; and position embeddings, where the word appears in the sequence. These three are summed together to create the final input representation. The input then flows through multiple transformer layers. Each layer applies self-attention to understand relationships between words, then passes the result through a feed-forward network for additional processing. Residual connections help information flow smoothly, while layer normalization keeps the training stable. This process repeats 12 times in BERT base, with each layer learning increasingly complex linguistic patterns. What's particularly clever about BERT's architecture is how it handles different types of input. For single sentences, it adds a special CLS token at the beginning and SEP token at the end. For sentence pairs, it uses CLS, then sentence A, then SEP, then sentence B, then another SEP. The CLS token becomes crucial during fine-tuning as it aggregates information from the entire sequence. The output of BERT is a rich contextual representation for each input token. Unlike static word embeddings, these representations change based on context. The same word will have different representations in different sentences. This contextual understanding is what makes BERT so powerful for downstream tasks. BERT's training is a two-phase process that's both ingenious and computationally intensive. Phase 1 is pre-training on massive amounts of text, and Phase 2 is fine-tuning for specific tasks. Let's explore how BERT learns to understand language without anyone explicitly teaching it grammar or semantics. Pre-training uses two clever, self-supervised learning tasks. The first is masked language modeling, or MLM. Imagine reading a sentence where some words are covered with tape. You'd use context to guess the hidden words. BERT does exactly this. Randomly mask 15% of input tokens and train the model to predict them. This forces BERT to understand bidirectional context because it needs information from both left and right to make accurate predictions. The second task is next sentence prediction, or NSP. Given two sentences, BERT must determine if sentence B logically follows sentence A. This teaches BERT to understand relationships between sentences, which is crucial for tasks like question answering and natural language inference. During training, 50% of the time sentence B actually follows sentence A, and 50% of the time it's a random sentence from the corpus. The scale of pre-training is staggering. BERT was trained on the book corpus, over 11,000 books, and English Wikipedia, about 2,500 million words. This massive dataset exposes BERT to diverse writing styles, topics, and linguistic patterns. The training process took days on powerful TPU clusters, consuming enormous computational resources, but creating a model with broad language understanding. After pre-training, BERT undergoes fine-tuning for specific downstream tasks. This is where the magic of transfer learning shines. Instead of training from scratch, we add a simple classifier on top of BERT's representations and train for just a few epochs on task-specific data. This approach achieves excellent results with relatively small datasets and much less computational time. The pre-trained representations capture general language understanding, while fine-tuning adapts them to specific applications. Now let's get practical. Understanding BERT's theory is one thing, but implementing it is where the real learning happens. We'll explore how to use pre-trained BERT models, fine-tune them for specific tasks, and integrate them into real-world applications. Thanks to libraries like Hugging Face Transformers, using BERT is remarkably straightforward. You can load a pre-trained model with just a few lines of code. For text classification, you typically add a classification head, a simple linear layer that maps BERT's output to your target classes. The beauty is that you're building on top of BERT's rich representations rather than starting from scratch. Let's walk through a sentiment analysis example. First, we tokenize our text using BERT's tokenizer, which handles subword tokenization and special tokens. Then, we feed the tokens through BERT to get contextualized embeddings. Finally, we use the CLS tokens representation for classification. During training, we freeze BERT's weights initially and train only the classification head, then gradually unfreeze layers for fine-tuning. For different tasks, you'd modify the output layer accordingly. Question answering requires predicting start and end positions in the text. Named entity recognition needs token-level predictions. Text similarity might use the CLS representation for comparison. The key insight is that BERT's versatile representations can be adapted to virtually any NLP task with minimal architectural changes. In production, consider factors like model size, inference speed, and hardware requirements. BERT Large gives better performance but is slower and requires more memory. Techniques like model distillation can create smaller, faster models that retain much of BERT's performance. The choice depends on your specific requirements for accuracy versus efficiency.